let's continue the morning session. Our next speaker is Shearing from Imperial College London, and the title of his talk today is Correlative Studies of SOFC electrode microstructures using FIB and X-ray techniques.
Thanks very much, Jake, and thanks again for the invite to come here. Today I'm going to talk about correlative microscopy of SOFC electrode microstructures, and I try to think about ways in which the work that we were doing was sufficiently distinct from the work that everyone else was doing that we weren't going to listen to 8 of the same talks today. So I'm going to be talking a little bit about focused ion beam work, but perhaps focusing more on some X-ray techniques that we've been developing over the past 18 months or so. I think Jake mentioned in his introduction there's really been some quite good progress with X-ray techniques in recent times, so hopefully touch upon a little bit of that as well. So yeah, correlative microscopy, a few focused ion beam case studies, and then looking at X-ray nano-CT, both lab and synchrotron experiments, and maybe a quick look at some feature plans as well. So obviously if we define our tomography platform as broadly by the voxel dimensions or the spatial resolution we can obtain and the volume we can analyse, then I think that most people would agree that to characterise SOFC electrode bulk microstructures, we're really kind of looking around this red area, which is sort of sub-micron voxel sizes and 10 micron cubed plus volumes you're looking at to get a representative structure at sufficient resolution. Obviously there's advantages to atom probe and electron tomography to study more fundamental stuff, effects at interfaces, and I think that's very interesting work, not something we'll talk about today. And then also conventional X-ray CT and mechanical sectioning certainly has its place in other fields, but perhaps not so much in SOFC electrode studies. So I think that the red area represents the area we want to be, and for me that's focused ion beam tomography and X-ray nano-CT. So X-ray nano-CT being distinct from conventional CT, and I'll talk about that as well. I don't think I need to give an introduction to focused ion beam slicing view. I guess a lot of people in the room are very familiar with these techniques. Obviously, a lot of the software that people developed, people in this room developed to interpret these microstructures, and a lot of the experimental methodologies I think are something that we should discuss tomorrow, because I think that's the area where a lot of the synergies are. So when James was talking before about writing code to get rid of little grey edges, then I guess we've all sat down for a couple of weeks and wrote code to get rid of little grey edges, and a lot of these problems are shared. So I think that's a great focus for this meeting, is to try and get some kind of idea of the way that all of our techniques correspond. Yeah, so obviously we have techniques for reconstructing and then extracting triple phase boundaries. Again, this has all been published, and I guess we all have our own slightly distinct ways of doing this. I think Nigel's maybe going to touch on it in a little bit more detail in the next talk, or maybe after lunch. So I just want to pick out a few case studies of the FIB work we've done. First of all, I want to look at some of the highest resolution studies we've done. So in this case, we took what we're calling a nano-ceramic. So we have a sort of nanoscale, roughly 100 nanometer plus particles of nickel distributed in this zirconia matrix, and the idea is to try and decrease the volume fraction of nickel you need to get decent conductivity in the surface structure, and therefore you try and avoid some of the problems with coarsening and these types of things. And we were able to reliably reconstruct the wires, so you'll notice that this isn't a porous structure, this is just nickel distributed in the zirconia. You can see very, very small balls, but primarily we're looking just to characterise the nickel distribution, and we managed to do that. And these particles are sort of 100 nanometers plus, so if we're looking at 10 nanometer voxel size, and we were rating 10 voxels per particle, something like that, and this was just an example of some of the smallest feature sizes that we characterised. Another example is combining tomography with EBSD, and it's good to see there's going to be a talk about this, dedicated to this afternoon. We've not seen much work on it really, and we kind of just did it as a proof of concept type study, but we basically took a nickel wire-set surface structure and using an FEI tool, just trying to reconstruct it. So it's an FEI dual beam with an Oxford Instruments EBSD detector, and just combining the EBSD collection with the focused ion beam milling. So here's an example of one of the EBSD maps, and you can see we've got reasonably clean kind of surface. You can see a little bit of streaking up the top here, and obviously, particularly for EBSD, you need to really take care to avoid that because that completely destroys your EBSD signal. But focusing on a small section within the bulk, we're able to reconstruct. So this is just obviously some of the crystals. But one thing that you can see is that we've got pretty coarse Z-plane resolution. So we have extremely rectangular voxels in this instance. And that's just because the time it takes to collect the EBSD maps is so long that we decided to sacrifice a little bit of the Z-plane resolution just to get the proof of concept studies done. And obviously, given time and sufficient tenacity, you could try and achieve cubic voxels. I think that's certainly possible. But nice things you can pick out, so you can see a twin boundary running through a nickel grain there. So there are some interesting things, and also for perhaps different materials, it gives you a bit of phase contrast as well, and that's difficult to come by. And then the last couple of applications of focused ion beam I'm going to talk about are the way we've combined these with modelling studies. So first of all, we looked at some microtubular cells. So Imperial College group of Jeff Kelsall is looking at novel phase inversion techniques for manufacturing microtubular cells. And these have highly distributed structures depending on their position within the cell. So you get these large finger-like pores which are supposed to accelerate gas diffusion, and then you get kind of electrochemically active regions which are supposed to promote sort of electrochemical activity. And so we just did some FIB reconstructions of a sort of section from each area to analyse what the triple phase boundary was there, and then that was combined with a COMSOL-based model to predict what the distributed current generation for those different regions were. So you can see, obviously, here's a section where we have one of these large finger-like pores, and here's the electrochemically active region. And yeah, using a kind of bulk parameter model in COMSOL, you're then able to predict the current voltage performance. The second model that we use is a volume fluid method, so taking some focused ion beam tomography data and then doing some level of coarse meshing to take some volume of fluid units and then modelling transport and electrochemical current generation in these structures. And this is, I think, a very core area of our work, but one that Nigel's going to talk about in much more detail, so I'll leave that to him. So one thing that I think probably a lot of people are interested in SOFC electrode studies is how microstructure evolves during time, how microstructure evolves during processing. Obviously, a lot of people are concerned with nickel coarsening and redox stability and these kinds of things. So we did try to do some preliminary studies using nickel zirconia anodes on a wire-stud electrolyte, and these were aged at various times, and we did some reconstructions to see if we could analyse any patterns corresponding to the aging effect. And basically, if we take the total percolate triple phase boundary distribution, we're struggling really to see any effects as we age these samples. So this is 100, 500, 1,000 hour. Now, it's possibly because we didn't do large enough samples or enough samples, and equally it's possible that this is because it's a destructive technique, and therefore you'd expect there are going to be some statistical variations in the material microstructure. And if we're looking at a dynamic sort of evolution process, I think it's quite difficult to decouple these statistical interferences from the actual microstructural evolution process. And that's where we got into looking at X-ray nano-CT, because X-ray CT obviously being a non-destructive technique. So nano-CT is a relatively new kind of invention. I suppose it's been at synchrotrons for almost 10 years maybe, and for a less amount of time in lab-based environments. But basically it uses X-ray optics to focus the X-ray before transmission, so you get a very nice parallel beam, and then after transmission it uses a zone plate to focus the transmitted X-rays before the CCD. And basically that improves the resolution by about an order of magnitude compared to conventional cone beam CT scanners. So in the X-Radius system that we've been using, and we've been working closely with X-Radius over in Concord, California, they use a condenser lens to focus, get parallel beam with a Fresnel zone plate to focus after transmission for the CCD. This gives a variable field of view between 15 and 65 microns, the lab-based source, and that roughly corresponds to voxel sizes of about 10 to 60 nanometers, something like that. And also these zone plate systems are compatible with synchrotron sources. So as I mentioned, you can see we have our source condenser lens, which makes a nice parallel beam before transmission. So we now have, because we're focusing the lens, we now have a field of view within the CT scanner, which is basically defined by this little cube here, and then focused again before we get to our scintillator detector. So because we have a field of view within this X-ray microscope, it's important that we think about the implications of our sample geometry. So based on a sort of standard parallel beam back-filtered algorithm that you use to reconstruct the X-ray data. So obviously you rotate the sample relative to an X-ray source, obtaining a sequence of transmission micrographs, and then use one of these algorithms to reconstruct the whole thing, and that gives you your equivalent slice data. But because we're looking at field of views of between 15 and 65 microns, we need to maintain the sample within that field of view in order to maintain the integrity of our data and also to optimize the reconstruction algorithm. Now, if we drift in and out of the field of view, you end up with an incomplete data set. This is perhaps comparable to TM tomography, some of you may be familiar with. You get this missing wedge type problem. And if you have a missing wedge, it introduces noise into your reconstruction, and it makes it difficult to try and get any phase analysis because you're no longer sure where your contribution from sample geometry and your contribution from sample phase has come from. So getting the right sample geometry is actually very important, but obviously with field of view of like 15 microns, it's not trivial. So we actually use a focused ion beam to prepare optimal samples for this. Basically a micro-manipulator system which we bolt onto the FIB, and then we have the gas injector system within the FIB. So we basically mill around a chunk, introduce our tungsten needle, platinum microweld, and you can see this is actually a transmission micrograph with a large field of view mode, and you can see that the whole sample is nicely fitting within that field of view. So we're then satisfied that we've met this criteria for reducing noise in the algorithm and for giving us some sort of assurance about the contributions from the geometry and the contributions from the phase. And then this nicely sits in the little sample holder, and that's what MD showed. So in lab-based systems, we looked at the pore distribution of a nickel zirconia anode. This is the large field of view. This is the high resolution mode, so 15 micron field of view. And we also did in the large field of view mode, which is like 65 micron field of view. So we're getting really quite large volumes here. It's about 40,000 cubic microns, which from the literature at the time when I wrote this, it was more than 2 orders of magnitude larger than the greatest FIB reconstruction that we'd seen reported. So if you're just looking at porosity or perhaps single-phase materials, and there's certainly advantages of using the lab-based nano-CT system, because you can characterize pretty large volumes with pretty decent resolution. However, you can see this is an individual slice from the tomography data set. You can see that whilst there is some phase contrast between the grains, it's also demonstrated in this 3D reconstruction here. You can see the grayscale contrast. It's not really sufficiently reliable from lab-based systems to be able to resolve the nickel zirconia contact and the triple phase boundary, which obviously we're all very interested in. However, it did kind of indicate that while maybe it is possible to try and isolate this triple phase contact using the X-ray sources, but maybe not in a lab-based system. So all these studies were done in a lab-based system with a fixed X-ray energy. If we use a synchrotron, we can vary the X-ray energy around the absorption edges of different materials, and that basically allows us to highlight different grains. So if we take the nickel edge, which is actually about 8.3 keV, if we alter the X-ray energy from the synchrotron above and below the nickel edge, it just highlights where the nickel is, and it's kind of a Zane's type, so X-ray absorption near edge spectroscopy type phase identification technique. But we can do this in situ at the tomography stage. So now we're getting decent phase contrast and the tomography at the same time. So this is just demonstrating that. So below the nickel edge, so we can compare these two grains. So below the nickel edge, this is where 8.1 kV, you're really not seeing hardly any contrast between the nickel and the zirconia phase at all. And above the nickel edge, you're all of a sudden switching on that nickel phase, and you can get pretty decent contrast. And that allows you then to do the full 3D reconstruction.
So what's the big scale?
Of this one, so this I know is 9 by 9 by 9 microns. This I'm not 100% sure, but it was in the 15 micron field of view mode, so I assume
particles are about a micron.
Okay.
yeah, ish. So I assume this is probably the length of the field of view, so about 15 microns. And this is 9 by 9 by 9 microns, which is most of the data. And we can see by using synchrotrons and using this absorption edge technique, then we're getting decent phase contrast, which is becoming comparable to the FIB-SEM technique. So if we take a look at a video that's going to take us slice by slice through one of the X-ray sequences. So this again is one of the samples as well that on top of a needle. This is the electrolyte section that you can see now. And then, so this is the electrode section coming up from the bottom. So again, we've managed to characterise the electrode-electrolyte interface, which is nice. As James touched upon as well, there's lots of interesting things that happen in the electrode-electrolyte interface. And also, we're trying to pause the video at an appropriate point. This is commercially available, off-the-shelf, wire-sent electrolyte coin cell. But we're actually seeing we're getting a load of defects in the wire-sent layer. So presumably this was perhaps tape cast electrolyte, and these appear to me to be sort of bubbles that are a artifact from the tape casting process. And yeah, sort of as we managed to capture those defects in the electrolyte at the same time as getting that electrode data and the electrode-electrolyte interface. And obviously, one advantage of the CT technique over the FIB technique is that you don't get the same streaking, you don't get differential milling rates and these types of things. So it's quite nice to be able to capture that in detail. And we were really surprised about just how many defects there were in this electrolyte. It sort of made me think about switching suppliers. And yeah, obviously once we've reconstructed the data, we can then use this for studies of microstructural homogeneity. And we basically, in a recent paper, took a bulk electrode and split it up into lots of different pieces. And obviously the smaller the sample is, you sort of move away from microstructural homogeneity and you discover heterogeneity, which just emphasises the importance of characterising a sufficient sample. And also, as James mentioned, there's increasing interest in these tomography platforms for lithium-ion batteries, and we recently published some work on X-ray characterisation of graphite electrode, along with Peter Jorgensen, and did some of the nice geometrical analysis. So here's what the graphite electrode from a lithium-ion battery looks like. Again, capturing quite a lot of microstructural detail there. And these lithium-ion guys didn't really have that much of a clue about what their electrodes look like, or at least they weren't talking about it. Maybe Panasonic knew and Sony knew, but they definitely weren't being public about it. And this is some of the tools that Peter talked about, looking at tortuosity and surface area and stuff for that graphite data set. Very quickly, recently a review article that's in press, a review of advanced microstructural characterization techniques. So International Materials Reviews, I don't know if it's available online yet, but if you want a copy, I'll happily send you one. And it talks a lot about FIB techniques, X-ray techniques, and their importance in electrode engineering, conclusions, acknowledgements. So thanks to all the people at Imperial, and also to Peter, being as always in the room. And thank you all for your attention.
Thanks for also sharing the nice new results that many of us haven't seen before. Are there any questions? question regarding your aging experiments.
Yeah.
Were they just aged in a furnace, or were they actually electrochemically performed for that number of hours?
They came from an industrial partner, so
Okay.
I'm not sure is the answer.
Yeah, okay.
I think they're aged in the furnace.
Yeah, from what I can see in the data, it looked like all the change happened in the first 500 hours.
Yeah, I think that from that data, we're not trying to take everything out of that data, because I think that you need to do a much more comprehensive study in order to be able to extract reliable, TPB evolution and these kinds of things. It was sort of just a proof of concept study, and as the X-ray techniques became increasingly available, sort of moving towards those for study rating.
Scott Barnett from Northwestern. If you're actually doing an in situ aging study in the synchrotron, is it possible that the intense X-rays could actually affect the structure evolution?
Well, one way we can. So, do you mean does the X-rays cause localized heating in the structure? So we know there's no localized heating from the X-rays. I don't know how you get migration induced by the X-ray. It's not something I thought about, but.
I just know a synchrotron source is incredibly intense.
Yeah, sure. Well, obviously, because it has a, so you get a lot of flux, but actually quite a low energy. It's because there's a crystal monochromator that we can tune the energy very exactly around this nickel edge, as I mentioned. So whilst there is a lot of flux, it is quite a low energy, about 8 kV, so an order of magnitude at least below most lab sources. I'll ask the X-ray guys and see what they say about that, but we do know there's no heating from the X-ray.
Maybe Henning can comment on this.
The X-rays. I would guess that you would have a local heating of the order of millikelvins. It's true that the synchrotrons have you can have severe problems when you have polymers and that sort of thing. But it's more to do with that you can generate free radicals. So you don't care about that in these materials at all. So I would hope that there would be zero. I have a question, if I may.
Yeah, sure.
Have you considered doing validation or experiment in the sense that you first do look at it at your sample with the signature and then do FIB on it afterwards to see what the results are?
So we've looked at the same bulk sample, so the same pellet, and done some FIB work and some X-ray nanoCT and compared the process measurements. And that's a pretty ambiguous comparison maybe, but they compared remarkably well. So we looked at the same X-ray sample in large field of view and in high resolution mode, and then a FIB section from the same pellet, and they compared very well. We've not actually got to the point where we've sectioned one of these things on a needle, but that is something we're looking to do.
James Wilson, Northwestern. Just kind of thinking about your sample and coursing effects. You might want to be careful that when you do the reconstruction, you almost look only at sort of the interior structure of that pellet. Because it's possible that, part of coursing that happens in nickel YC is you're constrained by the YC structure.
Sure.
And if you're at the edge, these nickel particles on the edge might behave differently just because there isn't material there. So I don't know.
Yeah.
I don't know if you've seen anything like that, but
well,
you might, if you just take the inner core, that would be fine.
As I mentioned, with the FIB stuff, we sort of stopped doing the FIB coarsening work a while back. So I think that definitely you run into the problems. If you saw on these micrographs that the electrode layer is actually very thin. So potentially there'd be something there, because obviously there'd be a differential across that thin electrode layer. With the needle samples, they're all bulk nickel wire sets, so there's no interface in the redox ones that I showed you.
I'm just talking about the sample itself. So you've got this little chunk on the end of the needle.
Right.
As you heat that up and cycle it, the nickel on that chunk near the surface might behave differently because it is an open surface, opposed to if it was in a bulk.
Just to follow on that, it looks like when you extracted the chunk with the FIB, you used pretty high milling currents.
Yeah.
haven't noticed the
So it's
microstructure
going to get,
surface.
you definitely get some beam deposition on the edges of that, and you can see that in the video. So when we're doing a reconstruction, we also take a central chunk, so we're not getting all the gallium and all other kinds of rubbish on the outside. I hadn't thought about the potential for differential portioning based on the edge compared to the middle.
I mean, if you've got a large enough volume, you can just crop out and just look at the core. Maybe. That was just something to think
Okay, it's time to move on. Let's thank Paul again.